When dealing with electrical circuits, safety is paramount. Always ensure the power is off and the circuits are de-energized before starting any work. One method to identify mated circuits involves energizing them and using an amprobe on the neutral conductor. This technique, while viable, requires caution due to potential hazards if not performed correctly. A more precise, though time-consuming, approach is to trace each circuit individually back to its origin. Single-phase circuits generally do not necessitate three-pole breakers. However, in three-phase systems or situations with significant load imbalance, using three-pole breakers becomes necessary. Incorrect neutral connections can lead to various problems. Firstly, overcurrent conditions and voltage imbalances can occur. Secondly, overloading the neutral conductor is a risk, potentially causing overheating and creating safety hazards. Thirdly, improper neutral connections can damage connected equipment and even pose a fire risk. To mitigate these risks, consider the following suggestions. If the circuits are part of a three-phase system or if there is a significant load imbalance, utilize three-pole breakers to ensure adequate protection. Instead of energizing the circuits for identification, consider employing a voltage tester or an ammeter. This allows you to determine the continuity and verify the correct connections between the conductors and the neutral without the risk of energizing the circuit. Once the circuits are correctly identified and connected, clear labeling is essential to prevent future confusion. If you have any doubts or uncertainties regarding circuit connections, it is strongly advised to consult a qualified electrician for guidance and assistance. An amprobe, also known as a clamp meter, is an electrical test tool used to measure the current flowing through a conductor without physically contacting or disconnecting the circuit. It works by clamping around a wire and measuring the magnetic field produced by the current, which is then converted into an amperage reading. The amprobe typically measures alternating current, AC, but some models can also measure direct current, DC. When using an amprobe, firstly, ensure the circuit is energized and carrying a load. Secondly, select the appropriate amperage range on the amprobe. Thirdly, open the clamp jaws and position them around a single conductor. Ensure the jaws are fully closed for an accurate reading. Fourthly, read the current value displayed on the meter. Ammeters are instruments used to measure the current in a circuit. They are connected in series with the circuit so that all the current flows through the meter. There are two main types of ammeters: analog and digital. Analog ammeters use a moving coil galvanometer to deflect a needle across a scale. The amount of deflection is proportional to the current flowing through the coil. Digital ammeters use electronic circuitry to convert the current into a digital reading. They typically have a higher accuracy than analog ammeters. To use an ammeter, firstly, turn off the power to the circuit. Secondly, break the circuit at the point where you want to measure the current. Thirdly, connect the ammeter in series with the circuit, making sure to observe the correct polarity. Fourthly, turn on the power to the circuit. Fifthly, read the current value displayed on the meter. Voltage testers, also known as voltage detectors, are tools used to check for the presence of voltage in a circuit or electrical device. They are designed to provide a non-contact indication of voltage, enhancing safety when working with electricity. Voltage testers typically work by detecting the electric field generated by the voltage. When the tester is brought near a live conductor, it will provide a visual, audible, or vibratory indication of the presence of voltage. Using a voltage tester is straightforward. Firstly, ensure the tester is in good working condition and the battery is charged, if applicable. Secondly, hold the tester near the circuit or device you want to test. Thirdly, observe the indication provided by the tester. If voltage is present, the tester will indicate it through a light, sound, or vibration. Three-pole circuit breakers are designed to protect three-phase electrical circuits. They are commonly used in industrial and commercial applications where three-phase power is used to operate motors, machinery, and other equipment. Three-pole breakers have three separate poles, each protecting one phase of the three-phase circuit. They are designed to trip all three poles simultaneously if an overcurrent or short circuit occurs on any one of the phases. This helps to protect the equipment and prevent damage. Three-pole breakers come in a variety of sizes and amperage ratings to accommodate different electrical loads. When selecting a three-pole breaker, it is important to consider the voltage and current requirements of the circuit being protected. A qualified electrician should be consulted to ensure that the correct breaker is selected. Overcurrent conditions occur when the current flowing through a circuit exceeds the rated capacity of the circuit components, such as wires, circuit breakers, and electrical devices. This can happen due to a variety of reasons, including short circuits, overloads, and ground faults. When an overcurrent occurs, the excessive heat generated can damage the circuit components, leading to insulation breakdown, melting of conductors, and even fires. Circuit breakers and fuses are designed to protect against overcurrent conditions by interrupting the circuit when the current exceeds a safe level. These devices are rated in amps, which indicates the maximum current they can carry without tripping or blowing. Voltage imbalance, also known as voltage imbalance, occurs when the voltages in a three-phase electrical system are not equal in magnitude or are not 120 degrees apart in phase angle. This can happen due to uneven loading of the phases, faulty equipment, or power system disturbances. Voltage imbalance can cause a variety of problems, including increased motor heating, reduced motor efficiency, equipment malfunction, and premature failure of electrical components. It is important to monitor voltage balance in three-phase systems and take corrective actions if imbalance is detected. This can involve redistributing loads, repairing faulty equipment, or improving the power system grounding. Neutral overload occurs when the current flowing through the neutral conductor in a circuit exceeds its rated capacity. The neutral conductor is the return path for current in a single-phase or three-phase electrical system. In a balanced three-phase system, the neutral current is ideally zero, as the currents from the three phases cancel each other out. However, in reality, imbalances in the loads connected to the phases can cause current to flow in the neutral conductor. If the neutral current exceeds the conductor's rated capacity, it can overheat, leading to insulation damage, melting of the conductor, and even fires. To prevent neutral overload, it is important to ensure that the loads are evenly distributed across the phases and that the neutral conductor is properly sized to handle the expected current. An ammeter is an instrument used to measure electrical current, which is the rate of flow of electric charge. The C unit for current is the ampere, often shortened to amp. Ammeters are essential tools for electricians, electronics technicians, and anyone working with electrical circuits. They can be used to measure the current flowing through a circuit, diagnose problems, and ensure that electrical systems are operating safely. Ammeters are connected in series with the circuit being measured, so that all of the current flows through the meter. There are two main types of ammeters: analog and digital. Analog ammeters use a moving coil galvanometer to deflect a needle across the scale. The amount of deflection is proportional to the current flowing through the coil. Digital ammeters use electronic circuitry to convert the current into a digital reading. They typically have a higher accuracy than analog ammeters. Circuit breakers are electromechanical devices designed to protect electrical circuits from overcurrent conditions such as short circuits and overloads. They are essential components of modern electrical systems, providing a safe and reliable way to interrupt the flow of electricity when a fault occurs. Circuit breakers are designed to trip or open the circuit when the current exceeds a predetermined level. This protects the wiring, equipment, and personnel from damage and potential hazards. Circuit breakers are typically rated in amps, which indicates the maximum current they can carry without tripping. They are also rated in volts, which indicates the maximum voltage they can safely interrupt. When a circuit breaker trips, it can be reset manually by moving the handle to the OFF position and then back to the on position. However, it is important to identify and correct the cause of the overcurrent before resetting the breaker, as repeated tripping can damage the breaker and the circuit. Fuses are another type of overcurrent protection device that are commonly used in electrical circuits. They consist of a thin wire or strip of metal that is designed to melt and break the circuit when the current exceeds a safe level. Fuses are typically used in low current applications such as protecting electronic devices and small appliances. Unlike circuit breakers, fuses are not resettable and must be replaced after they blow. Fuses are rated in amps, which indicates the maximum current they can carry without blowing. They are also rated in volts, which indicates the maximum voltage they can safely interrupt. When a fuse blows, it is important to replace it with a fuse of the same amperage and voltage rating. Using a fuse with a higher amperage rating can be dangerous, as it may not protect the circuit from overcurrent conditions. Ground faults occur when an unintended electrical connection is made between a live conductor and ground. This can happen due to damaged insulation, faulty wiring, or contact with a grounded object. Ground faults can be dangerous, as they can cause electric shock and fires. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults by quickly interrupting the circuit when a ground fault is detected. GFCIs work by monitoring the current flowing through the hot and neutral conductors of a circuit. If there is a difference of more than a few milliamperes between the two currents, it indicates that current is leaking to ground, and the GFCI will trip, cutting off the power to the circuit. GFCIs are commonly used in areas where there is a risk of water contact, such as bathrooms, kitchens, and outdoor outlets. They are also required by electrical codes in many locations. Short circuits occur when there is a low resistance connection between two conductors in a circuit, typically between a hot wire and a neutral wire or a ground wire. This can happen due to damaged insulation, faulty wiring, or contact with a conductive object. Short circuits cause a large amount of current to flow through the circuit, which can quickly overheat the wiring and cause a fire. Circuit breakers and fuses are designed to protect against short circuits by interrupting the circuit when the current exceeds a safe level. When a short circuit occurs, it is important to identify and correct the cause of the short before restoring power to the circuit. Damaged wiring should be repaired or replaced, and any conductive objects that are causing the short should be removed. Electrical codes are sets of regulations and standards that govern the safe installation and maintenance of electrical systems. They are designed to protect people and property from electrical hazards, such as electric shock, fires, and explosions. Electrical codes are typically developed by national or international organizations, such as the National Electrical Code, NIC, in the United States, and the International Electrotechnical Commission, IC, internationally. Electrical codes cover a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. They also specify the types of materials and equipment that are permitted to be used in electrical systems. Compliance with electrical codes is typically required by law, and electrical inspections are often conducted to ensure that electrical systems are installed and maintained in accordance with the codes. Qualified electricians are trained and licensed professionals who have the knowledge and skills to safely install and maintain electrical systems. They are familiar with electrical codes and standards, and they use specialized tools and equipment to perform their work. Hiring a qualified electrician is essential for ensuring the safety and reliability of electrical systems. Qualified electricians can perform a wide range of electrical services, including wiring, panel upgrades, lighting installation, and troubleshooting electrical problems. They can also provide advice on energy efficiency and safety. Electrical safety is a critical aspect of working with electricity. It is important to always take precautions to avoid electric shock, fires, and other electrical hazards. Firstly, always turn off the power to a circuit before working on it. Secondly, use insulated tools and equipment. Thirdly, never work on electrical systems in wet or damp conditions. Fourthly, wear appropriate personal protective equipment, such as gloves and safety glasses. Fifthly, be aware of your surroundings and avoid contact with energized parts. Sixthly, if you are not comfortable working with electricity, hire a qualified electrician. In the NEC, Article 250 covers grounding and bonding. Grounding provides a path for fault current to return to the source, tripping the overcurrent protective device. Bonding ensures that all metal parts are at the same potential, reducing the risk of electric shock. Article 300 covers wiring methods. It outlines the requirements for installing conductors in raceways, cables, and other enclosures. Proper wiring methods are essential for preventing damage to conductors and ensuring the safe operation of electrical systems. Article 310 covers conductors for general wiring. It provides information on conductor sizes, ampacities, and insulation types. Selecting the correct conductor size is crucial for preventing overheating and voltage drop. Article 400 covers flexible cords and cables. It outlines the requirements for using flexible cords and cables in various applications. Flexible cords and cables are commonly used to connect portable equipment and appliances. Article 408 covers switchboards and panel boards. It provides information on the construction, installation, and wiring of switchboards and panel boards. Switchboards and panel boards are used to distribute power to branch circuits. Article 430 covers motors, motor circuits, and controllers. It outlines the requirements for installing and protecting motors and motor circuits. Motors are a major source of electrical load in many facilities, and proper motor protection is essential for preventing damage and ensuring reliable operation. Article 440 covers air conditioning and refrigerating equipment. It provides information on the special requirements for installing and protecting air conditioning and refrigerating equipment. Air conditioning and refrigerating equipment often requires dedicated circuits and special overcurrent protection. Article 500 covers hazardous, or classified, locations. It outlines the requirements for installing electrical equipment in areas where there is a risk of explosion or fire due to flammable gases, vapors, or dusts. Hazardous locations require specially designed equipment and wiring methods to prevent ignition. Article 517 covers healthcare facilities. It provides information on the special requirements for installing electrical equipment in hospitals, clinics, and other healthcare facilities. Healthcare facilities require reliable power and special grounding systems to protect patients and staff. In regards to voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce lighting output, and increase energy consumption. To minimize voltage drop, it is important to select the correct conductor size for the load in the distance. The NEC provides tables and formulas for calculating voltage drop. In regards to load calculations are used to determine the size of the electrical service and the branch circuits needed to supply a building or facility. Load calculations take into account the connected load, the demand factor, and the diversity factor. The connected load is the total amount of power that is connected to the electrical system. The demand factor is the percentage of the connected load that is expected to be in use at any one time. The diversity factor is a factor that takes into account the fact that not all loads will be operating at the same time. Grounding electrode systems are used to connect the electrical system to the earth. The grounding electrode system provides a low impedance path for fault current to return to the source, tripping the overcurrent protective device. The grounding electrode system typically consists of a ground rod, a ground plate, or a metal water pipe that is buried in the earth. Bonding jumpers are used to connect metal parts of the electrical system together to ensure that they are at the same potential. Bonding jumpers are typically used to bond metal conduits, metal enclosures, and metal equipment frames. Surge protection devices, SPDs, are used to protect electrical equipment from voltage surges caused by lightning, power line disturbances, and switching transients. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. Arc fault circuit interrupters of size are designed to protect against arc faults, which are dangerous electrical arcs that can cause fires. Size detect the unique characteristics of arc faults and trip the circuit, preventing the arc from igniting combustible materials. Tamper-resistant receptacles, TRRs, are designed to prevent children from inserting objects into the receptacle slots. TRR have internal shutters that block the slots unless both prongs of a plug are inserted simultaneously. Tamper-resistant receptacles are required in dwelling units in many locations. The NEC Table 310.16 provides ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius, in free air based on ambient air temperatures of 30 degrees Celsius. The ampacity of a conductor is the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The NEC Table 310.15 B3 provides adjustment factors for more than 3 current-carrying conductors in a raceway or cable. When the number of current-carrying conductors in a raceway or cable exceeds 3, the ampacity of the conductors must be derated to account for the increased heat generated by the conductors. The NEC Table 250.122 provides minimum size equipment grounding conductors for grounding raceway and equipment. The equipment grounding conductor is used to connect metal parts of the electrical system to ground, providing a low impedance path for fault current to return to the source. The NEC Table 310.15 provides allowable ampacities of conductors based on conductor size and insulation type. Conductors must be sized to carry the expected load current without exceeding their temperature rating. The NEC Article 210 covers branch circuits. Branch circuits are the circuits that supply power to individual outlets and equipment. The NEC Article 220 covers branch circuit, feeder and service calculations. These calculations are used to determine the size of the branch circuits, feeders, and service needed to supply a building or facility. The NEC Article 230 covers services. The service is the connection between the utility power supply and the building's electrical system.